As if our logical concepts weren't difficult enough under the best of circumstances, it actually turns out that the way we defined these terms leads to interesting implications in certain cases. So in this little video, we're going to look at these special cases, and I must warn you ahead of time, this is one of those videos that you might have to come back to after Unit 2 or Unit 3, because it really is the case that these are special, and it really takes some time to understand these. So let's begin looking at some special cases of logical concepts. The first one has to do with validity, and due to the way we've defined validity, there are some interesting cases. Basically, there are interesting arguments to which it applies to, which maybe you wouldn't have expected. Okay, an argument with a conclusion that is logically true is logically valid, no matter what premise or premises it has. So let's take a look at a logically true sentence, either I am a burrito or I am not. I know it's silly, but if you look at the words, the logical words in there, either or, we've set up a scenario where it's impossible for this sentence to be false. It has to be true. Either I am a burrito or I am not. By the way, I am not a burrito. But this sentence has an interesting property. It just simply cannot be false. So if we set this sentence as the conclusion of an argument, it actually doesn't matter at all what set of sentences your premises or just premise consists of. It's going to be valid no matter what. Now remember, we defined validity as if the premises are true, the conclusion is also true. Now think about this particular case. The conclusion is such that it is impossible for it to be false. So if the premises are true, guess what? The conclusion is going to be true as well, because the conclusion cannot be false in this case. So whenever you have a logically true sentence as your conclusion, you're basically done. That argument is automatically valid. Okay, here's another interesting special case. Any set of sentences entails every logically true sentence. This is very much related to what we just looked at. So if you take this basic setup here, and instead of an argument, we treat it like a set of sentences that entails some other sentence. So in this case, let's just say we have a set of sentences. That symbol is called a double turnstile, and that just basically means logically entails some other sentence. So typically you're supposed to align all these vertically, on a single line, but it's just an example, so it's okay. In any case, if you have a logically true sentence, you can basically derive it out of anything. Literally any set of sentences whatsoever, you can derive a logically true sentence out of it. In fact, you can derive a logically true sentence out of the empty set, essentially out of nothing. So these are, it's kind of something that you just need to note. You can derive a logically true sentence out of any set of sentences. By the way, it doesn't stop there. Technically, you can derive all logically true sentences out of any set of sentences. So it's a weird case. So not only is it special, but it really is kind of a weird scenario here. Okay, number 3. An argument with premises that form an inconsistent set is always logically valid. So this is maybe a really weird case, but take an argument, how about this one, where the premises blatantly contradict each other. All oscillators are truculent, says premise 1. Premise 2 says some oscillators are not truculent. That is a blatant contradiction. So in one you say they're all this way, and the other you say, well, some are not this way. It doesn't matter what those words mean. What's important here is that those two sentences, 1 and 2, are inconsistent. They can't both be true at the same time. And there at the bottom, I have a silly conclusion, but guess what? Because the premises are inconsistent, this argument is technically valid. Here's why. The definition of validity, again, is if the premises are true, the conclusion is also true. But in this case, it is impossible for the premises to all be true at the same time. They form an inconsistent set. So we can't even test for validity. In other words, it's not valid, if that makes any sense. It's not the case that it's not valid, because it's literally impossible for all the premises to be true. So if something is not valid, of course it is valid. So the two nots basically cancel each other out. So I know this is kind of a strange situation here, but this is an important thing to note if you want to kind of summarize this in the following way. If you have a contradiction in the premises, you can essentially derive anything. And that will come into play a lot in Unit 3 and Unit 4. So take special note of that and maybe come back and revisit this video later on. Note, this includes any argument with a logically false premise. So we looked at one where there's two premises that form an inconsistent set. Technically, you could do this with this argument as well. Premise 1, I'm a burrito and I'm not a burrito. That, there's a contradiction there, right? So eventually we'll give you the tools so that you can tease those out. You can, write 1, I'm a burrito, and 1.2, I'm not a burrito. And that would be an inconsistent set. But basically any contradiction of the premises whatsoever allows you to derive whatever conclusion you want validly. So again, inconsistent set with regards to the premises, that technically valid by default. Okay. And the last two are related. All logically true sentences are logically equivalent. All logically false sentences are logically equivalent. So logically true sentences can simply not ever be false. So they're all logically equivalent. They're all always true. Same thing with false. They literally cannot be true. They're always false. So they're all logically equivalent in that they're all false. So these are kind of weird cases. And I think knowing all these is important to honing in, your logical concepts. I mean, basically, this is the highest degree of understanding these concepts. If you understand their special cases, then you basically understand these concepts very, very thoroughly. But I do recommend you pay special attention to 1 and 3. Really think about those, because those will be, basically they'll be with us time and time again, especially number 1 will pop up again in Unit 2, and number 3 will pop up again in Units 3 and 4. So pay special attention to those. You might wonder, why is this the case now? Up until this point, I've been saying, well, it's not enough to just memorize these things. You have to kind of understand their implications. To be honest, though, and this is why they call it special cases, you almost don't have all the right tools to understand why this is the case right now. So you might want to just take my word for it on this one. It will be easier to understand this once we take a look at truth tables and truth functions in Unit 2. But if you are really excited, the interested student can also read Chapter 1, Section 3 of the Logic Book, which I provide for you. I provide the link for you. So, by the way, there are many logic books, but note that there's only one, the Logic Book. So that should be able to answer your questions.